Okay, so we're doing a change of variables. We're going to change e to the x into u. We got to figure out what du is by finding, or sorry, dx. Through this, we found that dx was du over u, and that by changing to the variable u, we get this partial fractions problem with a common denominator of u plus 2 times u plus 1. And so now we know that all that numerator there has got to be equal to u. So what does it mean? A plus b has to equal 1. And a plus 2b. Hopefully you're tracking easily on this. This is a real easy one. So from that, we're going to get that b equals -1 and a equals 1, 2. However, whatever method you want to do to get that from that system of equations, to get b equals -1 and a equals 2, whatever way you want to do it. So I'm just going to check here. First equation looks good. Yeah, they look good. Okay, so then we rewrite this as so now this integral can be rewritten in this form as, or sorry, this form right here, 2 over u plus 2. Plus -1 over u plus 1. Easy. 2 natural log of absolute value of u plus 2 minus absolute value of u plus 1. But our original problem was in x, not in u. The purpose of changing it to u was to get a more manageable antiderivative. Once we get that antiderivative, now we need the answer in terms of x. So we're going to change it back from u back to x. So the purpose of the u is to make things easier, and then we're going to change it back. U is, yeah, everywhere there's a u, we're just going to put e to the x back, because that's how we originally defined it. Okay, anybody have a question?
Professor?
Yeah.
So if it was a definite interval, can we not just change the x's to u's whenever we're plugging in the numbers? So that we don't
Yeah, I'm going to show that on the next one. So the next one we're going to do another one, and then I'll show how it works with a definite. Yeah, but yes, that's a good question. Questions on this one? Okay, so here's another example of that. Okay, so do you see that any of the techniques we've covered before today might work with this? So what techniques do we have? Undoing the chain rule, what do we think? That's always our first guess, is undoing the chain rule. Definitely not, right? Definitely not. We don't have the derivative of the inside of another one, right? How about undoing the product rule? Maybe, but it might get ugly, right? It's not one of our common forms for undoing the product rule, but it might work. Okay, is it a rational function where we can do what, partial fractions? No, right? We need polynomials. We got the square root. That's what's. So this square root is really what's kind of messing things up here. It's kind of locking us in. It's not an ear. This is an integral sign. There we go. Okay. So this square root is kind of messing things up. It's definitely not a trig integral. There's no trig function. So how can we do a change of variables? What should we let u be? That might free this up a little bit to do something. What's that? Well, there's not really square root of x isn't really anywhere. Okay, so the whole denominator, or we could just do this interior, this whole interior here. Because if we're dividing by just the square root of one thing, that's a lot more manageable than the square root of a sum. The square root of a sum kind of locks us into not being able to do much. Okay, but if we let u be 1/2 x plus 1, that will take care of the denominator. So what else are we going to need? We're going to need to know what x is, and we're going to need to know what dx is. And then we can get this whole thing written in terms of u. That's the whole point, to rewrite this integral totally in terms of u instead of x. So we know what our denominator will be, square root of u. So in the numerator, we're going to need to get what x is and what dx is. Well, that should be easy. We know how the x and u are related. We just have to solve for x. So if we solve for x, we do it in our head, right? First step, subtract 1. Second step, multiply by 2. So we get 2 times minus 1, right? Right, so we're going to subtract 1. U minus 1 equals 1/2 x. And then x is going to be 2 times, or 2x minus 2. Okay, so then what's dx? So for this dx, now if we know what x is, dx is really easy. Dx equals? Oh, wait a sec. What did I? Yeah, sorry, 2u. Okay, so now, what is dx? If x is 2u minus 2, dx is 2 du. All right, now so we're home free. So you rewrite the integral. Okay, so do the first step, rewrite the integral in terms of u. You got everything you need. You've got the denominator, you've got what x is, and you've got what dx is. So you're going to rewrite, change the variable of the integral from x to u. Volunteer, who got it? Yes, sir.
Is it just what it looks like with the u put in?
So tell me.
So is it be 2 times 2u minus 3 squared over square root
Okay, what was the numerator again?
2
So-
times parentheses 2u minus 3 squared.
So we're you're trying to simplify as well. This is x, right? So if that's x, the first step would be that's x. So it's I think you ended up the 2 outside of the square. It sounded like.
Because dx is 2du.
Oh, so you were just saying the whole after simplifying?
Yeah.
Oh, okay. So I was gonna. Sorry. So yes, you may have been absolutely right. I didn't really pay attention. So this is the first step. And so then you pulled the 2 out in front. You said 2 times 2u minus 3 squared over square root of u du. Okay, so you just went right to the simplified version. Okay, good job. Okay, did it help? So the whole point of changing the variable would be it helps us to make progress towards being able to do the antiderivative. Did it help? He said a little. How can we go from here?
You can change the square root of u to 1/2 and then subtract the exponents to the numerator.
But you got different bases, right?
Or you can factor it out, or expand it first. Expand the numerator first.
Okay, yeah, so she's talking about expanding the numerator. Would that help? Middle term is minus 12u, minus 2 times that, right? Plus 9 over.
Oh, without this. Without this.
Can you see how we're going from here? What's that? Who's? Yeah, I just was trying to figure out who was talking. Yeah.
Split the fraction and take it.
Right. So we can split up this into 3 fractions, right? Think of this as a common denominator, and we're going to go backwards. We're going to split it up into 3 fractions, and then we just have power rule 3 times. See what happened? So if we split this up, so let's just throw this 2 out in front. So 4u squared over u to the 1/2 is 4u to the,
3 halves.
that's 4 halves, 3 halves. And then 12u to the, this is 1 minus a half. And then 9 over u to the 1/2. 9u to the, does our setup work? Okay, so now this is easy, right? It's just power rule. Just got to know our fractions, keep track of our signs, get our signs right, get our fractions right. But it should be easy, right? 4 times 2/5 u to the 5 halves. 12 times 2/3 u to the 3 halves. 9 times 2 u to the 1/2 plus c. So now let's multiply the 2 back in. So we don't have anything factored. We'll just have all terms. So it'd be, this looks like 16/5 u to the 5 halves. Check my math here. This is going to be, what was this? Was this 2/3?
Yeah.
It's like z/3. So this is going to be 48/3. Check my math. 36. Okay, but the problem was given in terms of x, not u. So, what do? So everywhere there's a u, now we're going to have 1x plus 1. So we're going to change it back. Here we go. Little pencil pushing exercise here. Concept writing.
Is it not 24? Is it 48?
2 times 4, 48 thirds. So I think it's 48, which this is just 16. So that ends up being 16, but 48 thirds is,
Okay, sorry, yeah.
you see it?
Yeah.
So this beauty is the antiderivative of this. Okay, so now the idea of what if we have a definite integral? So if we have a definite integral, suppose we were going from 3 to 7. So obviously we've got the quantity function, and we just need to find the total change from 3 to 7, right? So we have our quantity function. We're going to plug in 7, plug in 3, and subtract. So that would give us the total amount of change as x changes from 3 to 7 with a rate function of this ratio here. But we could, now if with a definite integral, we could do something different in that what are these values of u when x is 3 and 7? So when x is 3, u equals 5/2, is that right? And when x is 7, u equals 9/2. So what we could do is we could just, if we're doing a definite integral, we could stop with this u and evaluate it at the corresponding limits of u. So we could get the change for this quantity function from 5/2 to 9/2. And that would be the same total amount of change as this one evaluated from 3 to 7. Okay? So when you have a definite integral, you don't have to change back. You don't have to change back to the original variable. You can instead change the limits of integration into the new variable and then just evaluate that change in terms of the new variable. So you could do this one from 5/2 to 9/2. Anybody have a question? So we'll just we will have homework, but it won't be due till Wednesday at 1:30 when I see you again. Have a great long weekend. Be safe. So tangent to the fourth. Anyone have an idea to start this? Split it into what, Adrian? Good. Tangent squared and tangent squared. That's a good start. So, yeah, tangent squared and tangent squared. And then what? And so, is tangent squared 1 minus secant squared? Is that right? Plus? Plus. Okay. Is it not? Is it different than this? Is this right?
That's right.
This is
It should be negative 1 plus secant squared.
secant squared minus 1? Okay.
Oh,
Okay. And so from there we get two integrals. We get negative tangent squared. We can so the whole point of that is to then distribute these two, right? So then dx, so we can work on that one, and then we can work on this one, secant squared 3x, tangent squared 3x. And then we'll just leave that one. That's the easier one. You can do it. All right. Now what about just tangent squared by itself? Secant squared? No. So no, an integral is not. So tangent squared is, yeah, so the derivative of secant is not tangent squared. So you're mixing that up. The derivative of tangent is secant squared. So that doesn't work. But tangent squared equals secant squared minus 1. And I think that does it. That's just the opposite of that. So that's the roadmap for that one. Everyone see where you're going from there? Does that make sense? So then the other one that had the can I erase? Last chance. Please ask if I lost you. Going, gone. Okay, and then the other one is this one. Sine to the fourth. Same kind of idea. Actually, no, it's a little bit different. So sine of 7x to the fourth power. Did anyone come up with a way to...
You guys split them again for initially and then use them.
I don't think it works. Sine squared, so we get sine squared x times sine squared x, or 7x. So let's just try that and see where it leads us here. Sine squared of 7x times another sine squared of 7x, which is, we're going to do 1 minus cosine squared. So now if we multiply this in, sine squared, how do we do that? Got to just remember that. How do we do sine squared? Half angle identity, right? Just plain sine squared or just plain cosine squared, half angle identity. So that leaves us with sine squared times cosine squared. And I don't know how to do that.
Half angles.
Well, but then we just could have done that from the beginning. Then. Yeah. So, so if we want to try to like pull out, like we're thinking about undoing the chain rule, we just need one sine or one cosine, right? If we're undoing the chain rule. But when we do that, what happens if we pull out one sine? Then we're left with one sine, which we can't change into cosines. We need cosine squared to change it into. Sorry, we need sine squared to change it into cosines. So this doesn't, for getting this to do undoing the chain rule, like if I pulled out a sine 7x, then what I'm left with is sine 7x times cosine squared, and that's problematic because I can't write sine x in terms of cosine 7x. I can write sine squared 7x in terms of cosine, but I can't write just sine 7x. So in terms of undoing the chain rule, sine squared times cosine squared doesn't work.
But you could still get it. It's just.
And really, and what this is kind of analogous to is what we started with, right? So sine squared times cosine squared is basically the same integral as sine to the fourth in the first place. So we've kind of come back to where we started. So we want to kind of go back to the beginning and see if there's just a different technique that we could try.
Can we use 2 half angles?
And that's what you do. So if sine squared of 7x equals 1/2 1 minus cosine of, well, 2 times that. So it'd be 14x, right? That's a 14. So that's all of that squared. And then you just have a lot of algebra, but you can do it. So that whole thing, that's sine squared. And so now sine squared 7x, so it needs to be squared. So then from here, so you're going to multiply out. And when you multiply out, you're going to have a constant term, piece of cake. You're going to have a term with cosine, piece of cake. And then your last term is going to be cosine squared. And how do you do cosine squared? Half angle again on cosine squared, and then you got it.
Yeah. Where did you get the square from?
Because it's sine to the 4th, right? So everything inside here is sine squared, and sine squared squared is then, so I'm doing sine squared squared. So then I do the half angle formula for sine squared. Squared gives it to the 4th. So you'll have 3 terms, and you can do it. You'll have the constant term. You'll have a term with just plain cosine, 14x, easy. And then you'll have the last term with cosine squared, which you'll use the half angle identity again.